And so in this example, we're being asked the same thing: to eliminate the parameter, create a Cartesian equation of this relationship between x and y right here, and also sketch the parametric curve. In this case right here, I have these exponential functions. One thing that I could do, just to say, I'm doing it a little bit differently, but just to give this, to be clear about this, again, I like attacking this each, see if I can make this y a function of x by taking this. And what I could do is apply the natural log to both sides to get the natural log of x equals t, and then plug that in for t right here. And actually, that would work just fine. I'm going to attack this a little bit differently, but actually before I go about doing the elimination, I just want to do this quick check again about the x and y values. This is always nice to do in the beginning so that I don't make a mistake with my domains or my final sketch of my graph. So in this case, when t starts at 0, my x value becomes 1 because e to the 0 is 1. So x starts at 1. And then as t increases without bound, in this case, x also increases without bound. And so in this case, x will always just be greater than or equal to 1. There's no upper bound for this curve right here. And the same thing when I look at this. If I plug in t equals 0 into this, I'll get e to the 0 is 1. So y, the minimum value at t equals 0 for this function is 2, because 1 plus 1. So I have 2 is greater than or equal to y, or y is greater than or equal to 2. And actually in this case also, there is no upper bound because t is not bounded. This will increase. One interesting thing about when I'm analyzing this, I know that these are the lower values for when t is 0, because these are both increasing functions. As t increases, these values will also increase. So these t equals 0s are these lower bounds for the value of x and y. So now let's talk about eliminating the parameter. And again, as I had said, I could apply the natural log to both sides of this and plug that in. That actually works just fine. I'd end up with exactly the same solution that I would get in this case. But I want to just have you see this trick right here, because you might find a use for it moving forward when you have more complicated parametric equations. In this case right here, so I have x equals e of t, and I can kind of see e of t here. In fact, what I'm going to do is I'm going to rewrite this as, instead of e to the 2t, I'm going to write this as e to the t squared, which is an equivalent statement of e to the 2t. Because I'm raising this exponential expression to a power, I would multiply these exponents together. But then now what I can do, I have e to the t equals x. And so actually really quickly what I can do is replace e to the t with x to get that y equals x squared plus 1. So then after finishing that work right there, I realize that this parametric curve will have the shape of a parabola. Importantly at this point though, is I analyze my domain. And in this case, since this is it's y in terms of x here, this function, I can just think about my domain restriction here where x is greater than 1. And so I'll write that here real fast, is that my domain, and I'll write it in interval notation, is x is greater than or equal to 1. So it's from 1 to infinity. So then to go to sketch this, I know that this figure is a parabola. It's actually just a non-stretched horizontally or vertically x squared parabola, just shifted up 1. And so it will look something like this right here. And I've importantly used a dotted line for that because I know that I'm not going to use that entire curve. I'm restricted by this domain of 1 to infinity. So let's say 1 is right here. This point right here is 1, 2 on this graph. And again, I know the range for y goes from 2 to infinity and x is from 1 to infinity. And so this curve will look like this. And importantly right there, when I put the arrow, I kind of made note of it. But the fact is this parametric curve does go this way. It increases from left to right. And there's different ways of reasoning that. Part of my reasoning I was just talking about is that as t increases, both x and y increase. They increase in this direction right here. I could plug in t equals 0. That's actually where I got the 1 and the 2, saying that it starts right here at t equals 0. I could do a couple more test points just to make sure it's going this way. But to me, it's pretty obvious that it's going that way. So that is my parametric curve with the flow provided right there, the direction of the curve. And importantly, just to say again, this dotted line I'd put in was just to give me a framework for which to work. But this dotted line does not appear in the parametric curve. It's just this part of the graph right here.